I'd like to talk about assigning oxidation numbers, or commonly also called oxidation states, to different atoms in molecules. There are several rules, and you don't need to memorize these. I will give them to you on a test, but you do need to know how to use them. First rule is that the sum of the oxidation numbers in a molecule is equal to 0, unless it's a polyatomic ion, and then the sum of the oxidation numbers is equal to its charge. So, in a molecule like ammonia, NH3, the sum of the oxidation numbers is equal to 0. The oxidation number of nitrogen plus 3 times the oxidation number of hydrogen must equal 0. For a polyatomic ion, like the ammonium ion, the sum of the oxidation numbers is plus 1. That means that the oxidation number of nitrogen plus 4 times the oxidation number of hydrogen is equal to plus 1. We'll come back and do these as an example later on. Now, the oxidation number of an element is 0. So whenever you see an element that's not bonded to another element, in other words, if it's by itself or if it's with other atoms of the same element, then its oxidation number is 0. So you've seen some of these examples, specifically in single replacement reactions, which are all redox reactions. Oxygen gas, O2, all the diatomic molecules, that's their elemental state, and the oxidation number of each oxygen in O2 is 0. Whenever you see a metal all by itself, not in an ionic compound, then its oxidation number is 0. And some of the nonmetals are found as clumpy molecules, for lack of a better term, such as P8 or S4. But still, the phosphoruses in those compounds or sulfurs are all bonded to other phosphoruses, and so we assign an oxidation number of 0 to all of them. Okay, so the oxidation number of a monoatomic ion is equal to its charge. So, when you see a compound that is ionic and you know the charge on an ion, remember these are only for monoatomic, meaning single atom ions, then the oxidation number is equal to the charge of that ion. So, in the compound TiO2, titanium 4 oxide, each oxygen has an oxidation number of -2. We had to memorize that. Remember that oxygen has 6 valence electrons, so it needs to gain 2 in order to have a full octet. And so its charge is -2 and its oxidation number is -2. Because it's a neutral compound, then the titanium must be present as titanium plus 4. So its oxidation number is plus 4. So in an ionic compound, if you can figure out the charge on the ions, then you know the oxidation number of them. Okay. Now the next few rules only count when you're talking about compounds. So keep that in mind. In compounds, the oxidation number of group 1A elements is plus 1 and group 2A elements is plus 2. So, for example, in compounds such as sodium chloride, sodium is going to have an oxidation number of plus 1. It's really just an extension of the previous rule. Calcium chloride, calcium is going to have an oxidation number of plus 2. Okay, next rule. In compounds, the oxidation number of fluorine is always -1. Now, other elements in group 7A, such as chlorine, bromine, and iodine, they also have a oxidation number of -1, except when they are combined with oxygen or fluorine. So, for example, in the chlorate polyatomic ion, the oxidation number of chlorine is not -1, because it is combined with oxygen. So in those cases, you have to figure out what the charge is based on how many oxygens it's paired with. All right, this is because oxygen and fluorine are the most electronegative elements, and they can cause nonmetals to actually get a positive oxidation number. All right. In compounds, the oxidation number of oxygen is always -2, except when it is paired with fluorine. I think in the video, Hank also said that or in the crash course video, Hank said that in peroxide, it also doesn't have a charge of -2, but don't worry about that. And then finally, in compounds with nonmetals, the oxidation number of hydrogen is +1. In compounds with metals, the oxidation number of hydrogen is -1. So when you're talking about covalently bonded compounds with nonmetals, hydrogen is always +1. In compounds with metals, which you won't see, the oxidation number of hydrogen is -1. So let's go back up here. I hope I'm not making everybody dizzy doing this. Let's look at ammonia. We said that the sum of the oxidation numbers of nitrogen and hydrogen, 3 times hydrogen, is equal to 0. Well, none of the rules covered nitrogen, and that's because nitrogen doesn't always follow a simple rule. It's often found in more than one different type of oxidation state. So let me unhide what I had hidden up here. And okay, so but rule number 7 said that hydrogen is +1 when it is paired with nonmetals, and nitrogen is a nonmetal. So we can fill in the value for hydrogen here, and we can say that nitrogen plus 3 times the oxidation number of hydrogen, or +1, is equal to 0. That means that N plus 3 is equal to 0. We can solve that by subtracting 3 from both sides of the equation, and we end up with saying N is equal to -3. So we say the oxidation number of nitrogen in ammonia is -3. Now, that doesn't mean that nitrogen has a charge of -3. This is a way for us to keep track of electrons and where they're going in oxidation reduction reactions. So don't confuse charge and oxidation number, even though I often do. When I'm talking to you, I know what I mean, but nitrogen in ammonia is neutral, but it has an oxidation number of -3. Now, in ammonium, we can do the same thing. I'll unhide this. And here, hydrogen is still +1 from rule 7. So our equation is nitrogen, whatever the oxidation number on nitrogen, plus 4 times the oxidation number on hydrogen is equal to +1, because it's a polyatomic ion that has an overall charge of plus. So now our equation is, oh, I missed something there. Nitrogen plus 4 is equal to 1. So if we subtract 4 from both sides of that equation, we get nitrogen still has an oxidation number of -3. So now look on your page and on your handout and assign the oxidation numbers to the elements in each of the following 2 problems, question 1 and question 2. I'll post these on the problem set too.